Hello, everyone. Thank you so much for joining me today. My name is Shannon Holmes. I'm a medical physicist here at Standard Imaging, and it's my pleasure today to be able to tell you a bit about the Exradin Scintillator detectors. Before I get started, I do want to say thank you to all frontline workers in these, I guess, mind-boggling times that we're living in. I know I speak for the entire Standard Imaging family when I say that we really are proud to be supporting the heroes in the clinic, both the staff who are continuing to treat patients every day and the patients themselves. Cancer treatment is intimidating at the best of times, but right now I think it takes really an inordinate amount of courage to come in for a cancer treatment every day. So we honor those people. We're also extremely grateful for the workers who ensure that that we can have access to the things we need for our daily lives. So thank you to all of those essential workers as well. From our family to all of you. A little bit of housekeeping. I am recording the webinar today, so please, if you need to step away, there will be a recording link sent to you later. We do understand, especially for those who are trying to work while listening, that you do get interrupted. So we'll send you a link to that recording. If you have any questions through the presentation, please feel free to enter them into that GoToMeeting dialog box. I will do my best to answer those as they come up. So whenever you think of them, enter them in. Don't feel bad about interrupting. If you're not familiar with us, Standard Imaging is based in Middleton, Wisconsin. It was founded a little bit over 30 years ago and has grown from fairly humble beginnings into a QA provider where we design and manufacture a full suite of QA products for radiation therapy. It is a very exciting company to work with and work for, and we're proud to be here helping you out in treating patients as best as we all can to the best of all of our abilities. So the first question that I'm usually asked when we start talking about scintillators is why? Why would you want a scintillator? And the reasons I've mostly listed here. They can be made water equivalent for both MV photons and electrons, and the advantage of that really is that you're not perturbing the beam right there at the point of measurement. Detectors that are not water equivalent are actually disturbing the field right there at the point of measurement, which is why we have all of those correction factors that have to be applied for those effects. And with a water equivalent detector, a true water equivalent detector, you don't have those corrections. They can be made very small, so they can be used for those small fields that have been obviously a challenge for all of us over the recent years. They show dose and dose rate independence, so there's another correction that doesn't have to be applied or something that's not as concerning. They can be energy independent. That comes from that water equivalence as well, that your response doesn't change because based on energy, because you really are looking at the dose deposited in a water equivalent medium. That also means that your beam quality correction factor is unity, which is really nice, again, with the small fields as your energies change with source occlusion or lack of lateral equilibrium, things like that really affect some other detectors. The scintillators aren't showing that effect. There's a minimal temperature dependence. It's about 0.1% per degree, but as long as you're doing all of your QA measurements at approximately room temperature, then that's not something that you really need to consider. You can, of course, correct for that if you are concerned about it, but it's not a significant contributor to uncertainty in your measurement. They can also be used with MR Linacs. There are no metal components, no ferrous components at all in that scintillation fiber. The electrometers, of course, do have to be outside the 5 Gauss line in order not to have issues with those components. But the fiber itself can be used, it is completely MR safe, and we have had investigators use the W2 with their MR Linacs. So how do these work? We have an organic scintillating material, and with our detectors, the Exradin detectors, we've got a 1 millimeter diameter, 3 millimeter long active region for the W1 scintillator, and then there's an option as well for the 1x1 scintillator with the second generation, the W2. So ionizing radiation creates visible light within that scintillation portion, that organic scintillator, and then we have a PMMA optical transfer fiber that transfers that light, relying on total internal reflection, to our optics to collect the light. And of course, the amount of light generated is dependent upon the dose to that scintillator, directly related to the dose to the scintillator. And we can convert that optical signal into an electrical signal. The one difficult part about scintillators, and part of the reason that they haven't been made into commercial detectors until our detectors, is Cherenkov light. So this is an additional signal, kind of a stem effect that happens with these detectors, where the irradiation of that optical transfer fiber results in the generation of Cherenkov light. We do use a two-channel chromatic correction that's based on a publication from Matthew Guyot et al. In Medphysics in 2011. And I'll explain that here on the next slide, exactly what that two-channel correction provides. But that does give us a method to correct every single measurement for the effect of, or the contribution of the Cherenkov light, to remove that from the signal, so that the just the scintillation signal can be extracted. Scintillators are not absolute dosimeters. You can't send them into the calibration lab or to NIST and have them be calibrated. Because these are plastics, they do degrade slightly with radiation. The PMMA will turn yellow as it gets higher and higher doses of radiation, just like the plastics that you've got sitting in your clinics. And so it does require recalibration as the material accumulates dose. But you can do a calibration in-house, give it a known dose, and link that light output to actual dose value, and get dose results from it. It's just not an absolute dosimeter to be sent in for calibration. So in using the scintillators, that two-channel correction that I mentioned splits the spectrum up into what we call the blue channel and the green channel. So Cherenkov is a broad spectrum light. That's this line down here. The scintillation fiber that we use is a blue scintillator. So it peaks here in the blue region, although there is a tail that extends out into the green. And what we'd like to do is be able to separate this scintillation signal from the Cherenkov signal. And so we have you do two characterization measurements. One's called a minimum fiber measurement, where the fiber is straight out of the field, so you have as little fiber in the field as possible. And a maximum fiber measurement, where the fiber is wrapped around kind of in a spiral here, to be able to increase the contribution of the Cherenkov light without changing the dose to the scintillator. So the slabs that are shown here are the characterization slabs that are sold with the W1. They aren't option with the W2, but we do have a smaller bracket that can be used in a water tank for the W2 characterization as well. So once you make those two measurements, you can calculate, I meant to put the equation in here. You can calculate what's called a Cherenkov light ratio, or CLR, and that's the based on the change in signal in the green channel and the change in signal in the blue channel. You can create a ratio that says essentially then for subsequent measurements takes the signal level from the green channel, multiplies it by the CLR factor, and then subtracts that amount from the blue channel, so that you have the relative contributions between the two channels defined, and then that can be used to remove the Cherenkov signal from later measurements. If you want to do a dose calibration with your device, you can give it a known dose. We have a 10 by 10 field marked on those slabs for the W1, but give it a known dose in a known field size, known depth, and then there can be a dose conversion factor applied to those measurements as well. So the W1 I've mentioned a couple of times. This was our first generation scintillator. It has been on the market since 2014. It has that 1 millimeter diameter, 3 millimeter long active scintillation area at the tip of the fiber. Because it's been out this long, there are quite a few publications available that refer to measurements with this particular device. One of the most exciting to me is the recently published AAPM or joint AAPM and IAEA technical report series 483 report, which lists the W1 KQ as 1. This is one of the tables out of that publication, but it looks this way in pretty much all of them. This one happens to be the 10 MV table. It shows you equivalent square fields down to a 4 millimeter equivalent field size. This is just a partial list of the chambers and detectors that they have. Anything that, for those who aren't familiar with the report, if the values are not listed, that means that the committee deems the uncertainty from that detector to be too high. Either that or it was size, some limitation of the detector, but usually uncertainty for it to be used in those field sizes. But the W1 was included in this, and it's the only detector in any of these fields that has a correction factor of 1 across the entire table every single time it shows up. So I always have fun kind of showing that those tables, because it's reassuring to know that you're not missing something somewhere in these correction factors that, oh, I forgot to apply this. The limitation of the W1, though, is it is a single point measurement system. It was designed particularly for output factor type measurements, just single point measurements. And because the W1 is just the fiber and the optics unit, it does require something like our Supermax. It requires a 2-channel electrometer in order to perform that Cherenkov subtraction calculation. So we have a routine built into the Supermax where you can do those characterization measurements, save your factors, and then when you're using the scintillator after that, it will apply both that Cherenkov light ratio correction as well as the dose calibration, so that you get your measurement output already corrected just as a single value. With the W2, this was our second generation scintillator. It was released, goodness, is it 2 years ago now? Maybe only a year and a half, but a little bit more recently. This one has a user replaceable fiber, so you can detach the fiber at the back of the optics part. And it comes with both a 1 millimeter by 1 millimeter fiber as well as a 1x3. So if you're doing very small field measurements where that size, that volume averaging is super critical, you can use the 1x1. If you're in slightly larger fields and you'd like a little bit higher signal, you can use the 1x3. We created a dedicated unit for the optics signal collection and the electric signal processing for Cherenkov and dose calibration. That's called the Max SD. So because we were able to combine these into a single unit, we were able to decrease the electronic noise from all of those conversions, not having extra cables running around or out of the bunker. And so that's what enabled us to go down to that 1x1 fiber. We also increased the efficiency of our optics. You can do point measurements with this device directly with the Max SD. This will also convert that corrected signal back into an analog output, a single analog output that can be sent from the Max SD into the input signal channel on your water tank scanning electrometer. So as far as the water tank is concerned, it's something like a diode that's hooked up. You don't apply bias to it, but when the radiation turns on, your water tank electrometer receives an electrical signal proportional to the radiation that's being delivered to the detector. So it can be used with any water tank, and you can actually create profile scans or depth scans with it. One example of this actually is published by Indra Das's group out of NYU Langone. They had this figure out of their paper. They were looking at, in this case, a 1x1 field measured in water compared with a film profile as their ground truth. They also looked at the various characteristics of the fiber, including dose rate dependence and dose dependence. Not surprisingly, because we had seen these investigations with the W1 as well, they did not find any dose rate dependence or dose dependence. The fiber, the optical fiber, has not changed at all between the W1 and the W2. So we would have been really surprised if we had shown differing behavior here from what had been seen previously. The other kind of fun investigation that's been published fairly recently is a publication from Richard Popple's group out of the University of Alabama at Birmingham. And they were actually looking at patient-specific QA measurements for VMAT. And they looked at targets down to a 3 millimeter size diameter target, which was the smallest one evaluated, and found that their doses agreed with film. Even down to that smallest size. The mean difference between the W2 measurement and their film measurement for 60 patient plans was only 0.4%. So that also, or sorry, 400ths, I better read that properly. That also was a fun study to see. You can see on the right-hand side, this is the chamber plug from our stereotactic dose verification phantom. We have a marker fiber that's also provided with the W2 that has a BB right at the center of the active volume for the 1x1 fiber. So that's used for localization, and then it's replaced with the active fiber, which you can see water equivalent plastic and water equivalent plastic is hard to tell apart. This is a localization marker that's within that chamber plug as well. So that's about all I had for today. Thank you everyone for your attention. I didn't see any questions pop up as I was giving the presentation, but if you think of any, feel free to enter them now. You can also visit our website at standardimaging.com or contact your sales representative at sales@standardimaging.com if you would like any additional information or follow up about this. So thank you everyone. Take care, stay healthy. And if you have questions, I would happily answer them now. Faye asked a question about directional dependence. It is directionally independent, except for occasionally people have seen some dependence when you're, I think Richard saw some with a pure vertex field, if you're shooting straight down the fiber. The part of the reason for that, I guess, was traced to having the electrometer on the table. The Max SD is a little bit sensitive to the scatter radiation, and so if you make sure that that's at least a meter away from the field, you don't have those effects as much. The other thing that comes into play a little bit is the Cherenkov. Cherenkov has a preferential production angle of 45 degrees to the direction of travel of the electrons that are generating that signal. And because we're relying on the total internal reflection down the length of the fiber, irradiating in that pure vertex direction can create Cherenkov that's directed a little bit more in that direction down the length of the fiber, so you'll get more Cherenkov that way, as well as irradiating a greater length of the fiber. There may be some differences in the radiation dose damage along the length of that fiber, which can change the spectrum of the transmitted Cherenkov, Cherenkov light, particularly in this one. That can affect that CLR ratio. So that's one thing to look out for if you're doing a pure vertex field on this, that you may get a slightly higher uncertainty on your results. But for the most part, it is otherwise directionally independent. We do use, Steve asked if it's a photodiode or a PMT. It is a photodiode for our detectors, our optical detectors. Luca asked if there's possible to receive a recording. Yes, we will be sending out a recording of the webinar. Christina says, could you use the new fiber in a commercial water fountain phantom with the phantom electrometer? Yes, so you do have the Max SD kind of as an intermediary in that setup. So you put the fiber in the tank like you would align any detector. The Max SD would be just away from the tank off to the side, and then we have a short triax cable that would go from the back of the Max SD into the signal channel input on your water phantom electrometer. And as far as the water phantom is concerned, it just looks like a diode. It's none of the signal processing affects that scanning. The Max SD will output the integrated signal every 10 milliseconds, so it's relatively quick. But because it is a small signal, we do recommend that you scan slowly. So usually you would want to do point measure, step-by-step measurements, not continuous scanning, and do at least a 1 second measurement at each of those points. Steve asked, is the entire external part of the cable fiber optic? So the cable itself is that scintillation portion at the end that's potted to the PMMA optical transfer fiber or fiber optic, and the entire thing, remainder of that cable is PMMA, is that optical fiber. It does have a black sleeve over the outside of it that is a shield basically for ambient light, so that you don't get additional signal from the ambient light in the room. Let's see, the next question, Hannah asks, the field output correction factor for W1 is published as 1 in TRS 384, I think you mean 483. What about the W2? The W2 is identical. It is the same fiber. So any correction factors that are published for the W1 are applicable to the W2 as well. So Steve asked, this could not be used in scanning mode in a 3D water tank. You can, I think you mean continuous scanning. You can, it's a noisier scan, but the preferred method or the recommended method really is a step-by-step scan in your 3D water tank. Faye, if you would like price, please contact your sales representative. I'm not comfortable giving that, but yes, it is on the market right now. We can give you a quote. Does it work on any motorized water tank? Yes, it does. All of the ones that we're aware of, we do send it with an adapter sleeve because this is a very small detector. We know that most of your non-standard imaging water tanks, 3D water tanks or 1D water tanks, don't have holders for detectors this small, and so we do provide an adapter sleeve so that it can be used in one of your standard generic chamber holders in any of your water tanks. The question is, it's great for small field sizes. How does it fare for large field sizes? Can it be used for all? You get a much higher uncertainty for the larger field sizes. You may also get a slightly different spectrum on your Cherenkov depending on, again, that gradient of what field sizes you've used it in and how much radiation damage the fiber has received. So generally this really is a small field detector and is not so good for field sizes above, say, 15 by 15 or so. It's not the one detector to rule them all for every single measurement you need to take, but it is a very, very good detector to have for your small field. A few more questions, I think. Let's see. And the effective point of measurement is just the center of the fiber at the center of the active point or the active scintillation region. So it's, if I recall, 1.3 millimeters back from the tip of the fiber for the 1x1 and 2.3 for the 1x3 fibers. for the question on effective point of measurement, there is no offset. You don't have to lower the detector to account for that effective point of measurement because it is water equivalent. It is right at the center of the fiber. Faye asks if they don't have a 2-channel electrometer, can they use 2 electrometers instead? You can. You do have to do all of that math yourself in a spreadsheet. And really the main issue with using 2 electrometers is timing. So you want them to start and stop measurement at the same time in order for that to be an accurate measurement. If you're triggering both of them, that may be okay. Actually, it may be best. It depends on your signal levels and where your triggers are set. But it does get a little more complicated if you're trying to use 2 electrometers with the W1 instead of a single 2-channel electrometer. Let's see. Mahesh says they're trying to establish calibration capabilities for small fields at an SSDL using cobalt-60 with added conical collimators. Can I use the W2, which I just got to characterize the small fields, and what about field output factor correction for cobalt-60? You can absolutely use it for cobalt-60. It is energy independent for all of those MV photons, and so you can use the same correction factors that are used with the rest of the MV fields. You would do your CLR characterization in a slightly larger field. You can do a dose calibration if you want, and measure your small fields from your cobalt-60 unit for sure. Let's see, I just lost my spot. Where was it? Oh, okay, here we go. Ibrahim asks, is there an adapter so it can be placed in a solid water block? Yes, so depends on your solid water. We do have that characterization block that is sold, or that is included with the W1 and sold as an option with the W2, so that you can make measurements in a stack of virtual water or a water equivalent plastic. If you have a chamber plug for a different phantom, like for our SDVP phantom or our Lucy phantom, then we can absolutely drill those out for the W1 or the W2. The difficulty with a big slab of plastic is that a drill bit that size will tend to wander as you go deeply into the plastic. And so it's easier for those shorter plugs or smaller inserts like for the Lucy Phantom or for the SDVP. And then Christina asks, in the water phantom, do you have to connect also the max SD or the electrometer only? So the max SD is the dedicated optics and electronics for the W2. So the only input that the max SD will accept is an optical input. And then it will convert that optical signal to electronic signal it'll both the green and the blue channel. It will perform the Cherenkov correction, it will perform a dose conversion, and it will then output the signal, a relative signal strength based on the converted signal from that optical input. And that would be the input that goes into your water tank electrometer. So yes, you have to connect the max SD in order to be able to do any measurements with a W2, whether that's independent measurements with the max SD of just point measurements, or whether you're hooking the output from the max SD back to your electrometer with your water tank for scanning measurements to collect that scan with your water tank software. Can you use it for electron beams? Steve asks, I assume the Cherenkov would be very high. Yes, you can use it for electron beams as well. It's the same sort of effect of the Cherenkov being essentially a stem effect correction, but yes, you can absolutely use it for electron beams. I would probably recommend doing your CLR characterization in an electron beam so that you're as close as possible to the clinical setup that you're actually wanting to measure the dose from. But yes, you can use it in that. Steve says if you use it in a 200 kV beam, then there's no Cherenkov. Would that pose an issue? Can you turn off the Cherenkov subtraction? You can't actually turn it off. There are some quenching issues with kV beams, so you're correct, there's no Cherenkov, but the water equivalence isn't quite the same because of those potential quenching issues. So you can manually enter a CLR correction factor, and if your CLR correction factor is 1, but there is absolutely no signal in the green channel, then you would be subtracting 0 from your blue channel. You could also put it down at 0.002 or whatever you wanted to do to make sure that it's not affecting your measurements. So you could certainly do some research there, see what sort of results you get, but I can't guarantee the water equivalence down in the kV range. Yun Hao asks about protons. Protons also have a quenching effect with the scintillation fiber, or there is a quenching effect there. So there, I think, is some investigation going on with protons. Not directly, I'm not directly involved in that, but the question has been asked a few times. I know there's a research group down at MD Anderson that's looking into some proton work with scintillators. The corrections become more complicated because of that quenching effect. So I can't answer the question either about proton beam scanning, which is also listed in here. But the investigation still needs to be done on the proton side. Another question, for solid water phantoms, can we have a groove on opposite sides of 2 slabs? It would be better than a long drill bit. Yeah, and that's essentially what the characterization slab is. So it's a big 30 by 30 piece of acrylic or virtual water, depending which version you order, and it's a channel that's been cut in. I could go back to that slide. This one. It's that channel that's been cut into the top of a slab with a top slab that goes over top of it, so that the fiber itself is centered in that I think it's 2 centimeter stack once you put the top on slab on top. You do need to make sure that you've got proper buildup and backscatter to match your measurement conditions, because the Cherenkov, because it's generated by secondary electrons in a photon beam, is affected by the presence or lack of buildup and backscatter as well. So for proper characterization, you would want to make sure that you are past Dmax, you've got proper buildup and backscatter on that. Thank you. These are all wonderful questions, everyone. If you think of any more, I'll hang out for a little bit. But otherwise, once again, thank you very much for your attention. Stay safe out there. Make sure you take time to take care of yourself as well as the others around you.